So yeah, today I'll be talking to you about history matching. I'll be talking about climate modeling. I'll do a bit of introduction of machine learning, and I'll show you actually some results on a model called the L96 models. So I'll be going, slowly. This is actually a presentation which aims to present in simple words the technical aspects of doing history matching. So I'll be starting right now. So yeah, and as Rainer said, actually I was a postdoctoral researcher from UGA working at LSC IPSL and L'Océan IPSL in Paris, France. And there is my Twitter handle if you are interested. So yeah, let's start by a few words actually about climate modeling in general. So I'll try to do some kind of vulgarization of popular science, let's say. If you were actually at the MID conference in Strasbourg last November, you recognize actually this slide. So this was one of the slides I used for that conference. So here, actually, I wanted to say and congratulate again the Nobel Prize in Physics 2021 recipients, because actually half of the prize went to climate modelers, Manabe and Hasselmann, which was like an unprecedented event, because it was the first time actually that climate modelers get Nobel Prize in physics, which is really a big news. So why this is very, very important? Because actually works of Manabe and Hasselmann on climate modeling go for a long time. They're really, really old. For example, they show, this is, I'm just like taken as an example, two works from Manabe's team. So this is a recent picture of Manabe. For example, in this figure, this is a model coming from the 60s. So as you see, it's a very, very old model. This is a 1D model on the atmosphere. And actually what Manabe and his co-authors and colleagues, of course, show is that when you double and multiply by 2 and multiply by 4 the quantity of CO2 in the atmosphere, you see that the temperature at the surface increases. So this was really a very, very simplistic model, a 1D model, not as complex as the models we are using right now currently. So they worked again on a more complex, but not too much model. It was a 3D model this time. And they actually found the same results. They found again that if they multiply by 2 the quantity of CO2, they see that the temperature at the surface again increases. So here, just showing you that climate models always helped reliably predicting global warming since a long time. So you are probably asking here, because probably many of you are not experts, climate model experts. I'll try here to use simple words and to explain what is a climate model. So a climate model is actually a computer simulation. That's how you can see it. It's a computer simulation of the Earth's climate system. We are trying to simulate the climate system of planet Earth, including, of course, the atmosphere, several components, the ocean, the land, continental ice. And the goal is what? The goal actually is to use this computer simulation to try to recreate the past climate and also predict the future climate. So, of course, this is actually, if you know, and you probably know about the IPCC assessment reports, the last one was actually, the last one was actually went out on the 8th of August, if I remember well. So it was not very far in time. And you should know that many, a large part actually of the material that is used for this IPCC reports are coming from a project called CMIP, which is the Coupled Model Intercomparison Project, where the researchers analyze the simulations, many simulations coming from different modeling centers in the world, and they actually try to summarize all the publications that are explaining the result or describing the results coming from these simulations. So here, just to say that climate models are really a big part when trying to synthesize the materials in the IPCC reports. But concretely, the climate models are complex PDEs. For example, the most notorious example are Navier-Stokes equations, and you can see here an example of Navier-Stokes equations. And these complex PDEs are translated into what? Into lines of computer code, in general using Fortran language program, but not only, but it's actually the most used. So really concrete that is, this is it. I mean, a climate model, you must see it like this. You must see it as a big computer code with hundreds, thousands even, yeah, thousands of lines of codes. And of course, since we don't have like an analytical solution of Navier-Stokes equations, and of course, if you have an information about that, you can ask the Clay Institute to give you $1 million. So what we do actually an approximation, an approximation of these, the solutions of these equations numerically, okay? So there is a question here, which is about if you try to imagine doing or solving these equations on the whole globe, you clearly see that it is very, very difficult, all right? Because actually there's this question of spatial resolution. What is the spatial resolution you will consider? Since the complexity of the climate system, it's very, the climate system is very complex. And of course, if you try to model every point in the globe, you will need a lot of computing power. A model cannot possibly calculate all of these processes for every cubic meter of the climate system. So what climate modelers in general, they do is that they divide the Earth into a series of boxes, as you see here. And these boxes are called grid cells, okay? So this is an example for atmosphere, for a global atmospheric model. And as you see, actually, each box here is actually focusing on a part with some latitude and longitude and has a vertical grid representing height or pressure. And you can have the same on ocean models, right? You can also have boxes on ocean models. So each of these grid cells try to represent a lot of processes, as you see here. There are a lot of processes happening. So this question of spatial resolution is very, very important here, and we will talk about this later. So for example, there were a lot of models developed through time, and models started to become more and more better, and we now can increase, because actually it's just a matter of computing power and storage capacity. So now with more computing power, with more storage capacity, we can go further on resolution, or spatial resolution. As you see here, this is really very coarse, very smooth, and then you go from 500 kilometers to 250 kilometers, etc., until 110 kilometers here in the AR4, and you see that the resolution is better. So final resolution need, of course, more computing power, as I said. So the more grid cells, and this you understood this, the more grid cells you need, the more quantities you need to you calculate. If you have more grid cells, you calculate more quantities, which means more computing power, not very complex here. But don't forget that they also require massive storage capacity. Okay, I have here an example from the CSM model. When it is run for 55 model years with just 1/4 degree grid in the atmosphere, which not very, very high, and 1/10 degree grid in the ocean, it produces over 140 terabytes of output data. So you see that it's not just a matter of computing power, but also of storage capacity. But now we can, with climate model, currently, thanks to this development, we can run high resolution models and also try to incorporate more and more accurate physical modeling. This is starting to become really possible these last years. And for example, this picture from the GFDL model, it's not actually an image, a picture taken by a satellite or something, but it is coming from a simulation code. It is coming from a climate model. And so, yeah, what you are seeing here are really lines of code. But there is a catch. You understood here, I've said it too much, because actually this is one part which is very important for what I'll be saying next. Climate models are very expensive, and some processes are still hard to represent. For example, if you have a big grid cell, as I showed before, you do have a lot of processes happening in the grid cell. For example, if we take the example of the atmosphere, in the atmosphere, you do have clouds, right? You do have clouds, and sometimes the cloud is like smaller than the size of the grid. So you cannot represent it. So you miss the effect of the clouds. Same thing can happen in the ocean. You can have in the ocean actually a grid cell, but you do have sometimes eddies which are smaller than the grid cell in the ocean. So you need to represent them somehow, because you are losing here the effect of these processes. There is a solution for this. This is really a research field that is very, very developed. And one of the solutions is called parametrization. So what does parametrization mean? Here it means that instead of trying to force the resolution and having a really, really fine grid, you can stay in a somehow coarse grid, not too coarse again, and you can parameterize variables by using the computer code directly, rather than being calculated by the model itself. Okay, so you use some kind of equations and you code them and you choose some values for these equations to replace the effect of these parameterized variables. Here I'm showing some examples, and I've talked about some of them, like the reflection absorption by cloud, the effect of soil properties, the effect of evaporation, etc. So all of these you can, scientists or researchers did try to replace them with these so-called parameterizations. But then there is a question here. Parameterizations are one of the main sources of uncertainty, right? Because you are trying to replace a physical process with an equation that has some parameters, and you need to choose to know the values of these parameters, right? You need to select some values for these parameters. So in general, what scientists do is that they actually run tests with the model to find the values or range of values that allow the model to give the best representation of the climate. We will be talking about this because this is actually one of the main subjects of this presentation, and this is what we call climate model tuning. Okay, we'll come back to this later. So there is another question, which is suppose you have your parameterizations, you have some parameters, let's say alpha or beta or gamma, and you are trying to find a value for these parameters. How do you know that your model is good? Let's say good, or how you validate your model. So here the answer is quite straightforward. What we are using, we are using actually observations, real world observations. These observations can come from in situ data, can come from satellites, etc. So we run the modelers, or the climate modeler run the climate model, and then they calculate some kind of metrics and they compare them against the observation they have about this system. For example, average temperature, sea ice extent, etc. This is a figure, a very interesting figure from the IPCC last report, right, from 2021. And as you see, the observations here, so this is temperature, okay? So the observations are here in black. And you see that the models that incorporate the effect of the simulation of the human impact plus the natural variability of the model, you see that it is close to observation. This is in general used for attribution studies, okay? But when you see, for example, a model which has only the natural uncertainty, so that's, you see here that it's not close to observation. So with this figure, for example, you can say that there's a big human effect actually on the temperature, okay? So when you see these shaded parts, it's actually related to the uncertainty in the model simulations, okay? Because this is actually not the result of one simulation, but many, a number of simulations, okay? So uncertainty model, they come from, as I said first, the grid resolution. They can come from also the parametrizations, but they can also come from other sources like the intrinsic and uncertainty of climate, which is due to chaotic nature. So this part was actually just like a very simple introduction to climate models, okay? Just to make it easy to understand what I'm trying to do next. So the first part was an introduction to climate modeling in general, and also I mentioned climate model tuning, which I'll get back to later. Now in this second part, I'll try just to give some general ideas on machine learning and two applications on Earth system modelings. But here, please just pay attention only on the, on the idea, on general idea. There's no need to go into details right now, because anyway, I'll go into details when I'll start presenting my application, okay? So I'm sure now it's not, it's on now, it's really very usual now to see machine learning in a lot of applications which are really close to us and affecting us daily. If you have just a smartphone, you already have a lot of machine learning algorithms already affecting your life. That's for sure. So you know that machine learning is this science, or that this ensemble of techniques which use data to actually perform some tasks that usually were only performed by humans, or humans cannot perform it because it's very repetitive or needs a lot of money and a lot of efforts, okay? There are three big branches of machine learning. We'll be talking much about supervised learning because it's the one that has a lot of applications, in industry. I think 90% of the applications you do have operationally are coming from supervised learning. We'll be talking about supervised learning later, but just wanted to show a very broad, overview on machine learning techniques. So you can, for example, know classification. You all know what is classification, just classifying objects, and regression. And people who are working on statistical signal processing, for example, they know what is regression, not a big deal here. So in this presentation, I'll be more talking about regression, but I'll be mentioning also a bit classification. And then I'll be mentioning also clustering, but don't worry, I'll explain everything when time comes, okay? So this is just a slide, a general slide to show that there are three branches, big branches of machine learning: supervised learning, unsupervised learning, and reinforcement learning. We will not be talking about reinforcement learning here. We just focus on both here, supervised learning and unsupervised learning. Okay, what else I wanted to say? Yeah, for example, dimensionality reduction, it's a technique which is, very ubiquitous in geoscience. So if you already used, for example, PCA, or called also in the geoscience EOF, empirical orthogonal functions, you are already doing machine learning somehow, okay? So most of the things I'm showing here are not new things. The new avenue of machine learning is deep learning, but I'm not talking here about deep learning. I'm not using deep learning in this presentation, okay? So it's mostly traditional machine learning. So don't worry about this, we'll be talking about it later. So this is just an example of a supervised learning algorithm. Here, it's actually based on an algorithm called convolutional neural network, but I just like this image just to show you the idea of doing a classification task. You give actually, you do have a lot of examples, labeled examples, for example, labeled photos here of cats and dogs, and you do give the labels yourself. You do tell the machine learning algorithm that this is an image of a cat and this is an image of a dog, and then you let the neural net or the machine learning, you can see it as a black box here. It's not a problem, you can just see it as a black box. So the machine learning algorithm can give you the right, hopefully, of course, the right class, okay? But how this is actually done, this is what we call supervised learning. So supervised learning is the simple idea. So it's not really very complex. You can take a bunch of data you do have, which is data which are labeled, okay? We mean by label that you do have not only the data, not only the point, but the point and its class if you are, for example, doing classification. So classification is very simple to explain. So I'll stay with the classification example here, okay? So for example, these points are actually your images, your dog and cat and I don't know, fox images, and each one of them has a different color as you see. So each one of them has a label. For example, this is maybe an image of a cat and I give it the label cat, and the cat label is the gray color here, for example. So it is called supervision. It's called supervised learning because there is a supervisor, which is you actually, which is the person who is developing the machine learning algorithm, because they give the algorithm a training data set. And this is here where we talk about training a machine learning model. You are actually doing like you are doing, for example, with a baby, giving them, for example, an image of a banana and an image of an apple, and telling them that this is a banana and this is an apple. Okay, so I are trying to do this, of course, mathematically and with a lot of computer science code. You are trying to do the same with a machine learning algorithm. You are giving it the data, training a set, the desired output, and you are letting it train. This is what it's called here process. Well, I'm here really oversimplifying. So if you need or want more details, of course, I can give you more details with pleasure. So you train your machine learning algorithm, and then the machine learning algorithm tries to find the right class for each of your labeled data sets. So this is what we call the training phase. So you train your model to be good at classification, okay? And then what you expect is that your machine learning technique will take a new image and correctly classify it to the right class, okay? So here I just like really cherry-picked some examples from some of my previous works using supervised learning and also unsupervised learning. Unsupervised learning, as the name says clearly, it doesn't need a human supervision. It doesn't need labeled data set. So it's another way of doing machine learning. For example, when you are doing PCA, you don't tell your PCA algorithm to follow a label or something. It is actually a paradigm. There a cost function to minimize, and the PCA does the job. Okay, so this is one way to see unsupervised learning. So the first example was actually to learn what we call subgrid closures. And subgrid closures, if you want me to simplify it here, is supposing, you assume that you have a DNS, which is a direct numerical simulation, a high resolution simulation of some turbulent dynamics, okay? And this is very expensive too, okay? Well, not as expensive as climate models. Climate models are really very, very expensive. But still, you are trying to use a lower resolution model, and which is quicker to run, and try to model the difference between both. Try to learn how to actually add the missing component to be like close to the high resolution model. Okay, and this is an application where you can use machine learning, and even advanced machine learning like deep learning could be used, for example, in this in this problem. If you are interested, you can check the GitHub, for example, or the several papers we published on this subject. The second application, which I found it really, really cool here, it's on oceanography, where we use unsupervised learning. We use an algorithm called k-means. I'll be talking about it later, to find actually clusters in the ocean. And without any supervision, we're not supervising the algorithm. We just give it some kind of, I'll be not entering here in the details, but we give it some physical-based vectors and tell the algorithm to find clusters in this space. And when we go back to the physical space, we find that it actually finds some really physically consistent clusters here. And we use this algorithm to see the effect of climate change scenarios on the clusters, how they change if, for example, we multiply the quantity of CO2 in the models. So these were just some, as I said, cherry-picked examples. There are, of course, a lot of examples of the use of machine learning techniques in geoscience in general, and in numerical modeling in particular, and also in climate modeling. So now I'll be coming to the ML4 climate modeling tuning. So this is a collaboration with Julie Day from l'Océan IPSL and Venkatramani Balaji, who is a MOBGA recipient. So in the MOBGA project, which is called Hermes, we are using machine learning to help tuning climate models. Okay, and if you remember when I talked about tuning, it's this idea actually of finding a value or a range of values for some parameters. Okay, so now currently most of the modeling groups, they tune the parameters by hand. So yeah, they just try a number, they run their simulation model, they see if it matches with observation. If not, they just change the number and try it again and do this many times. So yeah, clearly it's very expensive. For example, for the IPSL model, it took like 5 years to find an acceptable tuning because it was completely done by hand. Okay, so our goal here is use ML-based emulators, and I'll be talking about emulators later, to replace the expensive climate model. Then what? Then find one or many good tunings or good sets of parameters. When we'll find them, we can then run the expensive model with these so-called good tunings. So this is really the summary of what I'll be talking about later. So now I'll start the part which is actually very focused on the work I did on the within the MOBGA project. So again, just a very simple figure. So you do have a number of parameters. You remember your climate model is just a simulation code, and you do calculate some metrics that you compare with observation, right? To do model validation, as I said, okay? So that's actually why I did the first part, so that you can easily follow this part here. So there's a very nice, and I really advise, and you can check this paper is really greatly written on the art and science of climate model tuning, and they discuss how it is important that each modeling group communicate their tuning strategy. For example, the IPSL team, they did this. They also communicated their tuning strategy in a paper now, very specific paper. And this is actually very useful, for example, when comparing models, different models on a specific metrics, because you do know that, for example, a model which was tuned specifically for this metric will be good, will be probably good for this metric. So it is really interesting to know what were the metrics, what were the strategies done when tuning the models. So you can, for example, think about this as an optimization problem. If you did optimization, you can just say, I will try to minimize this cost function because I do have an error. The error is what? Is the discrepancy between the metrics fx and the observation, right? And you are trying to find x that minimizes this error. But this is actually a bit problematic for climate sciences, because we are not trying to find one or the best set of parameters to solve this optimization problem. Why? And this is what they call in the paper that I showed you in the last slide, overtuning, because actually you will be very, very tied to the metrics you used for your optimization. Okay, so for example, if there were some processes that you did not use in tuning, your point will be very, maybe bad for these other metrics. Okay, so this is nicely said in the paper. They say that overtuning is a real concern and the raison d'être for Bayesian UQ methods. UQ stands for Uncertainty Quantification. Okay. So history matching is actually one of the techniques coming from this Bayesian uncertainty quantification methods. It is a surprisingly established technique used in a lot of fields like particle physics, molecular dynamics, etc., especially epidemiology. Also, I've seen this with some models with COVID, for example. And also astrophysics, a lot of works in astrophysics, and just very recently for climate science, which is a bit surprising here. It's really very recently that there are some works using history matching for climate science. One of the advantages of history matching is that it always has benefited from ML advances. Whenever there are new breakthrough and advances in machine learning, of course, history matching will benefit from it, and you will see this also in the next slides. So here, if you want just one message to take with you from this presentation about history matching is the following message. There is a different philosophy using history matching in contrast to pure optimization or pure calibration. There are a lot of terms. Here, instead of looking for the best set of parameters that solves an optimization problem, history matching will do what? Will use the observed data to rule out any parameter settings which are implausible. Instead of finding one good one, we will actually remove the bad ones and keep a bunch of good ones, okay? So I talked about like history matching and
Redouane?
Yeah.
You have about 10 more minutes, okay?
Okay, thanks. So history matching and ML, as I said, there are a lot of close connections between both fields. And you can here, for example, try to imagine with me the situation. You do have a climate models, and if you have like infinite computing power, what would you do? You would actually check every possible parameter settings for the input, right? For example, you know that parameter alpha is maybe between -10 and 10. We will just try, I don't know, millions of examples of this parameter alpha and run your model and check it. But of course, in reality, this is impossible. Climate models are very, very expensive to run. So you do need two things. First, what we call space filling designs. This means that you do have a space in your input that you do need to cover, right? If you have only one parameters, it's actually a line, but you do have in general many parameters. So you do have a hyper cube, for example, and you need to cover it. You cannot like sample it, do some kind of grid search. You need to sample it in an intelligent way. And this is a whole field of research and engineering. It's called space filling design, okay? Then what you need also is to replace the expensive simulator, right? You need to replace the expensive climate model. You cannot like run the climate model each time. So this is why you need to use what we call the emulators, which are rapid and cheap and based on machine learning. For people who are coming from the machine learning community, they know this field. It's called surrogate modeling, okay? So emulators do the following. It's easy, it's not very complicated. Instead of having the climate model, you do have some sort of a statistical emulator that gives you, that tries, of course, it's not perfect, that tries to give you the same metrics that would give the climate model, but and they have the uncertainties, of course, because they are not perfect, all right? But the advantage of statistical emulators is that they are very fast to run. They can use simple machine learning techniques that could be run, I don't know, on GPUs, for example, okay? So you can use them. This is the idea behind emulators, okay? But please remember, we use them only for the search, okay, for the search of the good parameters. And then when we will find one or two or more good set of parameters, then we can run the real one, the real climate models, okay? So please keep this in mind. The emulators are only used for this history matching, for the search of the good parameters. Maybe I'll skip, there are a lot of details, maybe I won't have time for this, but this is Gaussian processes. I'll be calling them next by just GP, are actually a machine learning technique, which does, for example, here regression, okay? They do regression, and they are actually why we are using them, because they deal with a low number of data, okay? If you've been hearing about deep learning, for example, or advanced, very advanced machine learning techniques, you know that they need a lot of data, but we cannot have them in the case of climate models, because simply we cannot run millions of climate model simulations. In general, we do have, I don't know, we do have like 50 or 100 maximum of simulations for some specific case, of course. And we do need machine learning techniques that can deal with a low number of training examples. The second good things about Gaussian processes is that they give you the uncertainty. You remember here, we do not need only the metrics, but we need the uncertainty. And the uncertainty in Gaussian processes are free, actually, are freely given with the algorithms. And it's actually a very nice and useful technique for our application here. So this is the summary of history matching. First, you do have an initial guess of parameter space. You do use the space filling designs, right, to select a number of points that will fill your space. You do calculate some kind of metrics, okay? For example, as I shown here, some temperature profiles, etc. It depends on your application. And then you can use the metrics to train, and you remember here, supervised learning. You train a machine learning algorithm. Here I'm using what? I'm using GPs, okay, Gaussian processes. In the end, since GPs are very fast, I can run millions of estimation of simulation. Of course, I'm not running millions of climate model simulations, but I'm emulating the climate model. So I can take a million point and have an estimation of what were the metrics, what would be the metrics and their uncertainty. And this is what can be used to calculate what we call the implausibility, which is, you can see it as a distance with observations, okay? I'll try to move very quickly. This is actually some of the examples of successful uses of history matching for climate model tuning, which are very recent. You see here 2020, 2017. Okay, for this case, it was for an atmosphere model. Okay, but the atmosphere actually, it has short time scales. So they did use some techniques with single model columns to afford to run several simulations. But this cannot be done for ocean, for example. For the ocean, it has a long time scale. You need to wait for a long number of years so that it stabilize and to calculate your metrics. So there are a lot of challenges especially in the ocean models. But the question that I'm interested in is about coupled models, where you have a lot of components in your climate models, and actually applying HM, which is history matching directly in coupled model, is still not explored. So here I'll come to the L96 toy model. Since I cannot like play directly with a big coupled model just to run experiments on the HM, I started with a toy model, which is quick and rapid, and I can play with it easily, okay? So I took the L96 model, which is a periodic system of KODEs, ordinary differential equations. It has two levels. So as you see nicely here in this video, you do have a variable which has actually slow dynamics, the blue here, X, and it is coupled with a variable, with a bunch of variables, actually with a number of variables of Y, which have fast dynamics. And we can use this model to do an analogy with coupled ocean atmosphere models, where the atmosphere have fast dynamics and the ocean slow dynamics. So the goal here is what is use HM for the tuning of these parameters that you see here, H, C, B, and F. okay? And you see them several times in the equations. So this is what I actually done. I've chosen the metrics as long-term time means to mimic climatological quantities. The ground truth is this one, 10, 1, and 10, and 10. Okay, so I generated the ground truth. I assume that the observations are coming from the ground truth without noise, just to check. And then I use the code, which is a mix of Python and R code. And these are my metrics, which are justified by energy conservation constraints. If you are interested, you can check Schneider et al. Paper. Sorry, I'll be moving very quickly because time presses. So yeah, this is, if you remember the pipeline of history matching, this is what I did here. I have an initial guess of parameter space. For example, f is between minus 20 and 20, okay? This is just like a random, I just took minus 20 and 20. I'm supposing here that I don't know too much about these parameters. I only know that C is positive because actually C depends on a ratio, on a time actually ratio. So it's time, it's positive, okay? Then you do a sample LHS is one technique to do space filling design. As you see, for example, you try to fill your space, okay, as much as you can, but you cannot generate a lot of data. So you generate just, in general, this is a rule of thumb. You take 10 multiplied by the number of parameters. I do have 4 here, so I'm generating 40 simulations. Then you run your real L96 model. You build your training data set for the emulator. You can use PCA to reduce the number of dimensions here. And then you use actually your GP, which are Gaussian processes, one per output, and train them so you can calculate implausibility. So these are some kind of visualization of the results. Okay, this is what we call a Neuraloid plot, not ruled out yet. Okay, please just focus with me on this part so that we can go quickly. So this is, as you say, it's actually a 4-dimensional space, right? We have 4 parameters. We cannot represent a 4-dimensional space. So what we do is represent 2D spaces, a bunch of 2D spaces. This one, for example, is the 2D space of FC. Okay, one point here means that F and C are fixed, but B and H can take a lot of values. Okay, so here quickly, and you can understand it from the colors. The red parts here are the parts where the implausibility is not good, actually. So these are the part where you do not need to look. You must not actually need. You must not look for the parameters, okay? And the green and yellow parts are the parts which are kept by the history matching. If you remember, we are trying just to remove the bad parts and to keep the good parts. And the black point here is the ground truth, which you see it's on the nice part, good part. So I did try history matching on the L96. Firstly, I tried just with the, as you remember here, this initial guess, and this is what it gives for the wave 1 until wave 6, because you can do it many times, an iterative process. So you can see in the end, in wave 6, we do have a remaining space of 0.02, 3%, a 2% space. We went to a space where we are trying 1 million of simulations to a really reduced space of 2% of that initial space. So the question, and I'll be finishing with this part here. The question is, what do we do with this Neuraloid? So this is actually an open question. It depends heavily on the computational budget. Because actually, if you do have, for example, this part here, would you have this Neuraloid here? You do know that you have a number of simulation, which is 2% of 1 million. You can do the calculation. It's maybe 2,000. So how can you select a good one? If you do not have a good computational budget, for example, for a high complex coupled model, you can maybe just run 2 or 3 simulation. What you can do is run a clustering algorithm on this space here, okay? You do a cluster to find these clusters, and you see them, I mean, by your eye, you can see that there are some clusters here. When you run, for example, k-means, which is a classical clustering algorithm, you can find that actually there are 2 clusters, and these are the centers of the clusters. So if your computational budget is very low, and you have only, for example, just two simulation to run, you can take, for example, these two centers. But if you do have more computation budget, of course, you can select more or select just randomly from the Neuraloid space. Okay. And then as I said, you go back to the real model, you run the real model, and you check if it actually matches observation, and that was the case here. Okay. So yeah, I will maybe go very quickly to the end. So this is, if you add domain expertise, you'll find that it is better actually to constrain the initial space, because the initial space is very big in the first simulation. So that's what we did here. We found again two clusters, but we found actually that one of the clusters here has a center which is very, very close actually to the good solution. So you feel that you are really doing this constraint. These constraints on the initial space help you very much. So these are the lessons learned. History matching is a powerful tool that can assist and not replace, of course, the expertise of domain-based tuning. Setting a computation budget in advance is very important and plays an important role in the final result, because you do check if you still have a budget to run more further experiments. And this is very important to know in advance before running history matching. And of course, incorporating as much domain expertise as you can is really helping also history matching, because the space of search becomes smaller and you help also history matching in the process. And of course, there are a lot of open questions that we can discuss maybe in the question and answers. And these are the conclusion of these presentations. It's about uncertainties in climate simulation in general, which are substantial in part due to parametrizations. Machine learning, as you probably now seen in other applications, not only this one I'm showing here, it offers a lot of promising opportunities. And history matching is an ML-based, machine learning-based technique to accelerate and improve calibration. And of course, here I'm showing it how applying it to an automated model can help you actually move to a real climate model, like what I'm trying to do now with the team in L'Océan and other collaborators on the IPSL new model SIMP7. And yeah, thank you. Thanks a lot for giving me your time. And sorry again for going for more than 45 minutes.
Okay, no problem. Thanks a lot for the interesting talk. If there are questions, then please raise your hand, put it into the chat or the question and answer tool. And yeah, I will then either read out the question or give you the chance to talk. I saw that Venkat Ramanian raised his hand. There sorry, I just had my.
No, that was a mistake. I was trying to clap. Sorry.
Okay. Good. Yeah. Thanks. Okay. Then maybe I have first. I don't know if this question is relevant, but how would you actually include changes in the data itself? So, for example, what I'm thinking about is that, for example, temperature measurements 100 years ago were probably not as precise as they are now. For example, in the ocean, people were using this thermometers, which had this mechanics of like turning around, and so we do know the deep sea temperature, for example. The measurements are, I think, less precise than what we have today, where there's a lot of effort going into calibrating these things and everything. How would you?
That's a really good question. I'll try to answer it, and if maybe Balaji have another answer, that would be helpful too. So what is good? I'll be answering it from the eye of someone who does history matching. Okay, what is good with the history matching is that you do calculate this implausibility. If you remember here, it is this kind of I'll try to show it again. Yeah, this kind of distance with observation. Okay, and if I understood you, Rainer, you are telling me that maybe observations are not as good, for example, in a period and in a null period, right? What you can do actually is add in other uncertainties here in the denominator. This denominator, you can add also not only just the error of your emulator, you can also add an error, an estimation of the error on observation, okay? So if you already have some estimation of the error of your observation, you can include it here. And you can also include an error on the discrepancy if there are like, structural discrepancy or biases in your model, you can also include it here. So the history matching is really very flexible for this kind of cases.
Okay, thanks a lot. Other questions? Yeah, there's one by Christina Richards. Christina, please go ahead.
Hi,
Hey,
this is so far outside of my field, but I can't help but wonder when I see these climate models that are all based on physical measurements, how you can account for the response of the biological system in the earth, because we know there are these feedback loops. So as, for example, there's more carbon, there are certain organisms that are going to suffer from that and other organisms that are going to be able to contribute to cycling the carbon. So I'm just wondering, I mean, I know this is kind of a guessing game for anybody, but I can't put the two different types of information together. We're trying to figure out how the biology on the planet is responding and also contributing in terms of just metabolic processes. I don't know if you've thought about those types of things that are kind of hard to predict at this level, or if there are people who are trying to model the uptake of carbon and the deforestation and all of that interplay between major biological systems. Is that at all on your radar, or?
Actually, I do not have a lot of information about this. Surely there are a lot of people working on trying to add biogeochemical, right? Yeah, surely, but really, I don't have like names on my mind on people who are working on that, because really my field of work is doing statistical modeling. I mean, I use the climate model as given to me. For example, it goes from the climate modelers. They did put all the scientific knowledge they have. And then my job is trying to do the history matching to find some good parameters
to make it more accurate.
Yeah, exactly. The modelization itself is done by the climate modelers.
Yeah. Okay. So before it gets to you.
Yeah, exactly. Yeah.
Okay. Julie has.
Is it okay if Julie steps in?
Yeah, of course.
Great.
I promoted
Thanks.
her to.
Yeah. Thank you
Julie,
very much.
please.
Can you hear me?
Yes. Great.
Great, thanks. Yeah, I'm the climate modeler in charge of preparing the configuration for Redouane. I'm not the only one. There's a big group of people there. And indeed, we try to factor in all possible processes relating biological activity and carbon uptake, for example. Now, you know the complexity of those. And the fact that most of the times they rely on observations and not on physical laws. So the fundamental of climate models is to actually resolve equations that we know for sure. We know them for sure, yet the resolution is very complex. This is why there is uncertainty. But it's a physical law that we know that we try to resolve. And I know by experience that the biological models are very different. They're not built on laws much of the time. I mean, you can have constraints, but it's not resolving partial differential equation like it is for climate modeling. So we try to factor in those processes. The complexity of climate model has increased a lot. And anytime you add one of those processes, there's actually a parametrization attached to it. And so the calibration technique that Redouane is working with is precisely on the fact of factoring in all the uncertainty in those representations, the uncertainty, the observations as well, because indeed it is very different. The certainty in a measure of SST 100 years ago and yesterday is very different. Same for all the parameterizations we are doing. So the issue is that as soon as you increase complexity in climate model, you increase the number of parameters that you have to calibrate. And it's extremely important to understand if we increase uncertainty in the climate projections at the same time, or if we reduce it. And the technique of history matching is one of the only one that we foresee now to make this calibration more objective, faster, avoiding overfitting, which would be a disaster, and yet increasing our understanding.
Cool. So you're relying on people to first incorporate the biology into the model before you're trying to optimize how your modeling fits with the actual data. So there's, yeah, it's a complex problem. Pretty fascinating. It's really hard to think about this stuff when you're a biologist working on the ground in local populations. Like, how do you scale up?
Yeah, maybe I can also give my view on this. I work on zooplankton in the ocean, and so for the ocean, the system models, they normally use models which are called NPZ models, NPZD. So they have phytoplankton, zooplankton, detritus, and maybe also bacteria. And so the huge diversity we have in the ocean is I put into these compartments, and they are all, I mean, all the zooplankton organisms that exist, they are all just parameterized with one or very few equations which should cover the mean of the zooplankton. And so what is going on is then to go into more details here and split these groups up to also get to more to get to more precise predictions. For example, phytoplankton, you can also have nitrogen fixing organisms and some that don't. And so splitting those into two compartments will already make the models, I think, more precise, but then also more complex and more hard to run. And so that's and doing the whole biological diversity is, of course, not possible. Okay, those are questions. Sorry for this.
No, it was wonderful. Thanks for adding that, Rania.
Maybe I have another question. It seems in your plots that you also, how do you deal with local minima, so to say? It seems that sometimes you have two possible solutions, or they are here on the lower right. You have two green fields separated by red fields, and so you might be lucky to land in the right patch if you really do that.
Yeah, of course. That's a good remark, because actually, as I said, the history matching only removes the bad configurations, right? So it keeps local minimums. Yeah, I'm not saying we will find the global minimum here. So it keeps all the local minimums, okay? And then what can the climate model do is run the expansive simulation using this bunch of local minimums, and what I'm trying to experiment with is using an ensemble of these simulations. I mean, with several local minima, you can run several climate models and then use an ensemble and just look at the mean and look at the covariances and the uncertainty of these models. But yeah, as you said, of course, here local minimum can stay in the Neuraloid, in the green area.
Is there a maximum how many parameters you can evaluate? Because if hundreds of parameters interact, then is that
actually this is depending on the computational power and the budget you do have. For example, if you can run 100 simulation, you can just take randomly 100 set of parameters from this green area, from this Neuraloid area, just randomly.
Yeah. No, I meant in the history matching process. Is there a maximum of parameters you can? I mean, the four parameters you check here, they will interact.
Okay, I see. No, there's no. I mean, maximum. No specific maximum. I mean, I used 4 parameters because the Lawrence 96 has 4 parameters. So that's it. But for we are trying now to check with the coupled models, or just start with ocean models, and you can see, for example, there are like tens, let's say tens, not hundreds, but tens of parameters. So the only limit you have is computational power again, okay? Because it trains the Gaussian processes. There are a lot of calculations happening. So if you do have a lot of parameters, let's say 100 of parameters to find, it's not impossible, but I'm not sure it will be, I mean, done in a reasonable time. I'm not sure about it. And I haven't seen this, I mean, in other papers from other domains. In general, they don't surpass, let's say, 30 parameters never seen more than 30 parameters.
Okay, yeah. Okay, further questions? If not, I have one more, but not so related to the exact talk. So, okay, you said, or I said it as well, that you are now working for the IRD, and I've seen that you will then work on or that it's related to also providing climate predictions for developing countries, etc. So can you go a little bit more into detail what you will do there in your new position?
Yeah,
For example,
yeah,
which region you will also work?
Yeah, actually, since I just started, in December. So the thing is, we do have some with IRD, we do have some areas which are very, let's say, prioritized. For example, West of Africa. So in West of Africa, let's say, for example, Senegal, Cote d'Ivoire, for example, as an example. Sorry, I'll come back.
Okay, I have to mute someone.
Yeah, sorry, it's just that my wife is working from home too, so I need maybe to change just to finish. Okay, so yeah, I've been saying, yeah, so there are some prioritized countries for IRD, for example, Senegal and Cote d'Ivoire. And what we'll be doing is helping scientists there, I mean, try to leverage the CMIP6 models, for example, and send them some kind of indicators of which are related to climate change. For example, if there will be some kind of decrease in precipitation in, let's say, 50 years in the future. So for this, what I'll be doing really concretely is using statistical techniques first to actually improve the models we do have and improve the outputs of the models. I will not be running again the models. There are some models which are already there, the CMIP6. Try to do bias reduction or bias correction. Try to do also downscaling for the specific regions, okay? Because the grid is coarse and you do need a grid which is fine on the country you are interested in. So there's another technique here which is called downscaling. And then I do have some, like, it's not really side projects, but not as prioritized as what I said now. For example, doing history matching to find improved models for these specific regions, because they do have some metrics. There are some metrics that they are interested in. For example, fisheries. Fisheries are very important for Senegal, for Mauritania, for Morocco too. So doing a metric on a metric specific to the needs of fishermen there would be very interesting for history matching, for example. So there are a lot of projects actually ongoing, and yeah, of course, I'm very excited